Welcome back to the second part of P2. We're going to talk now about, well, among other things, set notation and the properties of real numbers. So let's get right in. We're actually going to go pretty quickly through the properties of real numbers. I might put in a few extra examples now and then, but honestly the book documents this pretty well. There's not a lot I need to add. The big three properties of real numbers are the commutative, associative, and distributive properties. You can see them right here. The commutative properties of addition and multiplication tell you that addition and multiplication are operations that can switch their order. If you add A to B, it'll be the exact same operation as B plus A. 3 plus 4 is the same thing as 4 plus 3. Or 7 plus 3 and 3 plus 7. Subtraction doesn't work that way, although it can be quite similar. The trick with subtraction is that it's not commutative unless you rewrite it as an addition. So like 3 minus 7 is not going to be the same thing as 7 minus 3, but if I wrote it this way, 3 plus negative 7, then that's going to be equal to negative 7 plus 3. If you rewrite it as an addition, then it is commutative because, as we said, addition is commutative. And similarly for multiplication. Multiplication is commutative, division is not, unless you rewrite any division as a multiplication. So for example, 6 divided by 3, not commutative, but if you rewrite it this way, remember that when you're dividing fractions, you can take a reciprocal and multiply. So now you have 6 times 1/3, and that's commutative, because 1/3 times 6 is the same thing as 6 times 1/3. Associative properties just tell you that you can throw up parentheses and perform operations of more than 2 terms, or factors in the case of multiplication, in really any order you want. You can do the 2 and the 4 first, you can do the 4 and the 7 first, and in fact, because of the commutative properties, you can do the outer edges first as well. And associative properties for both addition and multiplication. Distributive properties tell you how addition and multiplication work together. As we've seen many times throughout developmental mathematics courses, if you have something multiplied on the front of a parenthesis, you can distribute it through. And that's what this says. Either side of the parentheses, it will distribute through. Now the properties of negatives. These are all fairly straightforward if you've done much arithmetic before. If you multiply a number by a -1, it will flip the sign. If you multiply a negative by a negative, you will get a positive. If you multiply different signs, you will get a negative. If you multiply the same sign, both negative, you will get a positive. If you distribute a negative through a parentheses, it will flip both terms. These tables are all copied straight from the book, so you can actually look them up in section P2 if you'd rather. Moving on, properties of fractions. Here's that one we just used a second ago. If you want to divide fractions, you invert, take a reciprocal, flip the second fraction, and then multiply. To multiply fractions, you multiply across the top, multiply across bottom. You can also sometimes do some simplification beforehand, because you can cancel out any common factors, or a better term would be reduce away the common factors. And if you're adding or subtracting two fractions, if they have common denominators, you can just add straight across the top. If they don't, then you've got to get a common denominator. That one they just multiplied, but often you can find a smaller common denominator than you've got. Number 5 here is talking about reducing. If you have a common factor on top and bottom, that basically becomes 1. 2/3 times 1 is then 2/3. Upshot is, of course, you can divide common factors into the top and bottom of a fraction to reduce. And this is saying you can cross multiply to clear fractions in a proportion like this. We'll have a more formal version of this later in Chapter 1. They often introduce proportions in pre-algebra courses because they're so helpful for applications. They're all about scaling. Alright, the order property of real numbers. Now, all of the real numbers are ordered. That means if you look at any two of them, they must have one of three relationships. So if you have A and B, real numbers A and B, A either has to be less than B, A must be greater than B, or A is equal B. Be careful when dealing with negatives. Some of the problems in this section will ask you to look at two numbers like 3 and 5 and write the correct relationship between them. Well, I mean, this one would be less than. And if you had something like -2 and 4, I mean, clearly every negative number is less than every positive number. Less than to greater than flows left to right on the number line. That's the real idea to remember when you're looking at negative numbers. So like -4 and -7, you might be tempted to say -7 is greater than -4, but that's not the case. Because if you look at a number line, I'll make a rough one here, -7, -6, -5, and then -4. You can see here -4 is to the right of -7 on the number line, therefore -4 is greater than -7. It's a little bit counterintuitive, but you just have to think about the number line. Which way does it flow, left to right? If you're dealing with fractions or in decimals, like say if you're comparing 3/7 to 0.14, I would just convert them both to fractions and then get common denominators. So let's see, 0.14 you can write, see, that's tenths. This position is the tenths, this is the hundredths. So the way to convert decimals to fractions is you just write the number 14 over the number represented by the last decimal position. So this is hundredths, so this is 14 over 100, and then I can reduce that. That is 7 over 50. So now all I got to do is get 7 and 50 to be common denominators. I don't think they have any common factors, so it'll just be 7 times 50. So 3 over 7 times 50 over 50 gets me, rewrite the problem down here, I'm comparing 3/7 and 0.14. 3/7 times 50 over 50 will get me 150 over 350. And then, let's see, to convert 7/50ths to 350ths, I'd have to multiply that by 7 on top and bottom. So that would be 49 over 350. And then clearly 150 is bigger than 49, so it flows this way. So 3/7 is larger than 0.14. You could also try and get decimal equivalents, but sometimes the decimals might be very close together, so you might not know. If you can get them to common denominator, it's just which numerator which top of the fraction is larger. Moving on. Sets. So first we're going to define a set. A set is just a collection of objects, and those objects are called the elements of a set. Probably should have made that bold since that's an important term. So for example, 2 is an element of the set of natural numbers. See, we saw that in the last lecture. Some notation. This is the element symbol. That means B is an element of S. So here's an example. 2.5 is an element of R. R represents the set of real numbers. When it's a double-barred R like that, that's the traditional symbol for the real numbers. This means not an element. This symbol means B is not an element of S. So square root of 2, which is an irrational number, is not an element of Q, which is what's traditionally used to represent the rational numbers. And here's a special symbol we'll see from time to time, in the homework as well. That denotes the empty set. Generally, you'll see it when you're doing a problem and they'll ask, what is the solution set? And if there's no solution, you'll just do the empty set symbol. Some more notation. This is about the union. If S and T are sets, this symbol is read S union T. It's the union of S and T, or the collection of all elements in both sets, ignoring duplication. So, looking at this example, 5, 6, 7, 8, 2, 4, 6, 8, the union is just all elements in either set. Notice I only wrote the common elements, 6 and 8, once. That's what I mean by ignoring duplication. It's a similar symbol for intersection. The intersection of S and T is the set of only the common elements. In 5, 6, 7, 8 and 2, 4, 6, 8, the only common elements are the 6 and the 8. Thus, S intersect T is 6, 8. Set builder notation. Sometimes it's not so convenient to write out every element in a set between two curly braces. In the last problem we did when we looked at S and T, both of those sets had 4 elements. But what if you had a set that had 100 elements? Well, it might be better to look at a shorter way of writing it than individually listing every one of the 100 elements whenever you want to deal with it. Instead, you might use something more like this. This is called set builder's notation, and it makes use of a condition to describe a large set of numbers, or at least a set of numbers. So this is read all x such that x is an integer and x is between 0 and 7. And you can see then that these are the exact same sets. These are all the integers between 0 and 7, not including 0 and 7. And this says the same thing. Now, arguably this is a little bit shorter to type out than this, but it wouldn't be if this were all integers between 1 and 2,000. This would be about the exact same length. It would just be 1 to 2,000, whereas this one would now have 2,000 different numbers in it. Be much longer. So it's a very handy notation for certain situations. This vertical pipe here, it's found right above the Enter key on most keyboards. It doesn't look like a vertical pipe. It looks like almost a colon with elongated dots, but it's usually right above the backslash. And it is just read in the notation as such that, x such that. So it should always generally be in the set builder's notation whenever you type it out. Here's a bit of a comparison between interval and set builder notation. Intervals are sets like this, where you have every number between two endpoints is in the set. In set builder's notation, you just write it like that. You have a left endpoint and a right endpoint, and you put x in between them with inequalities. But we also have an interval notation that's arguably even more concise. In interval notation, you just write the left endpoint, the right endpoint, and then depending upon how your ends work, whether they're solid or open dots, you will put parentheses or square brackets. So if you'll notice here, this is the interval of everything from A to B, but not including A itself and B itself. So for interval notation, you use parentheses if you're not including the endpoints. On the other hand, if you are including the endpoints, like here, then your set builder's notation will have less than or equal, because that's of course how the inequalities work. For interval notation, if you want to include the endpoints, you've got to use square brackets. Then, moving on, this is just a mixture of the two. Notice it has one endpoint that's not included, one endpoint that is. So that's how you would write it with interval notation. And moving on, this is an infinite interval. It has one side going off to infinity to the right. Does not include its left endpoint, but it does stop there. This would be all x such that x is greater than a, or a is less than x. You could write it the other way as well. X is greater than a. That would be fine to write instead of a is less than x. It conveys the exact same information. And here's how you would write it using interval notation. You just have the left endpoint, a, and the right endpoint is now infinity. Now, a special note about using infinity as an endpoint, since you can't actually reach infinity unless you're Chuck Norris, you must always have a parentheses on infinity. And that's specifically positive infinity. So it's going to be the right endpoint. If you're going to the left to infinity, that's negative infinity. So here we have negative infinity up to right endpoints. And then on this last, it's just showing that you can also express the real numbers, the set of all real numbers, as negative infinity to infinity. Every number between negative infinity and infinity. That's pretty clearly the real numbers. All right, let's keep going. Some properties of absolute value. Not a lot here if you're already familiar somewhat with absolute value. Absolute value basically makes things positive. It's the upshot. It's actually the distance function. If you take the absolute value of a number, it really gives you the distance of that number from 0. So for example, the absolute value of 5 is 5 because on the number line, it is 5 units away from 0. Same thing for negative 5. Here's just some properties of what to do when you have different operations inside. You can distribute it through a multiplication. You can also distribute it through a division. And I believe our last slide is up next. Distance between points on a real line. Like I said, the distance between 0 and a number is just the absolute value of that number. If you want to find the distance between two numbers, well, the difference between the two numbers is just their subtraction. But that's a signed difference. And when you're talking distance between points on a real line, you don't really care about the direction you were going, negative or positive. So you still subtract them, find their difference, but then you take the absolute value. Because then this b minus a is also going to be the exact same thing as the absolute value of a minus b. If you were looking at, say, the distance between 3 and negative 5 on the number line, well, you would do absolute value of 3 minus negative 5. And that would give you 3 plus 5 in absolute value, which would be the absolute value of 8, or just 8. Also, if you had set it up the other way, negative 5 minus 3, you would have got the same thing, because then you would have got negative 8 inside the absolute value, which then would come out to be just 8. All right, I think that's going to finish us up on this section. So the next video, we'll just do some exercises. I will see you, talk to you then.